Take a composite number like 120. Crack it open, and it shatters into smaller pieces until you're left with its mathematical bedrock, prime numbers. You could split it into 12 times 10, or you could divide it into 15 times 8. It doesn't matter. Reducing those branches to their indivisible roots always leaves the exact same primes, 3 2s, 1 3, and 1 5. This consistency has a name. It is the fundamental theorem of arithmetic. The theorem states that every integer greater than 1 has exactly one unique prime factorization. If you have done any basic arithmetic, this uniqueness feels obvious. But in mathematics, intuition is a dangerous substitute for proof. Prime numbers are the multiplicative foundation for analyzing integers at any scale. Before we can use them as a reliable coordinate system, we have to prove this unique structure actually exists. To do that, we have to abandon our assumptions. We must rebuild the mechanics of numbers from their first principles, starting with the basic rules of divisibility. Treating prime numbers as a rigid, universal DNA requires a flawless structural proof. Without it, the foundation of integer arithmetic remains a highly educated guess. The fundamental rule of this math is divisibility. The rule is strictly defined. An integer a divides b only if there exists another integer c, such that a times c equals b. That works for clean multiples, but we immediately hit a complication. What happens when a does not divide b perfectly? This diagram lets us visualize the problem geometrically. We can map the multiples of a as evenly spaced markers across an infinite number line. Any random integer b that drops onto this line faces a constraint. It must either land exactly on a multiple, or it falls into the empty space between two multiples. We define this physical gap mathematically as the unique remainder r. This formalizes into Euclid's divisional rhythm. b equals a times q plus r. And because b fell between two specific markers, r is strictly bounded. It is greater than or equal to 0, but strictly less than a. That specific boundary on the remainder guarantees that every single division calculation yields a strictly unique quotient and remainder. There is no ambiguity. This simple algorithmic remainder gives us immense utility. It allows us to repeatedly divide numbers to find their greatest common divisor, which is a necessary step in relating any two integers. This Euclidean property is what leads us to Euclid's lemma, the rule that if a prime divides a product of two numbers, it must divide at least one of them. This lemma is the structural bridge that makes unique factorization a logical necessity. Divisibility provides a rigid geometric and algebraic framework that maps the location and relationship of every single integer, which raises a crucial question. Is prime factorization guaranteed to be unique, or is that an accidental quirk of the number system we happen to use? Let's test it by building an alternate mathematical universe. We will call it set E. Set E contains only positive even integers, 2, 4, 6, 8, and so on. Odd numbers do not exist here. Within this specific universe, we must redefine what a prime is. Here, a prime is simply an even number that cannot be factored into two other even numbers. Look at the set, 2, 6, 10, 14, and 30. In the real world, these are composite numbers, but in universe E, they act as indivisible primes. You cannot split 6 into two smaller even integers. Now, let's drop the number 60 into this restricted universe to see how it breaks down. The first factorization path is straightforward. 60 splits into 2 times 30. Both 2 and 30 are primes in set E, meaning this is a complete prime factorization.
But look at the second factorization path. 60 can also be split into 6 times 10. Since 6 and 10 are also locked primes in set E, this is another complete prime factorization. We have achieved two completely different prime factorizations for the exact same number. The mere ability to break numbers down does not guarantee uniqueness. The certainty of the fundamental theorem in our standard integer system relies on Euclid's strict rules preventing this exact mathematical chaos. Because the division algorithm and Euclid's lemma prove prime factorization is unique, we can treat a number's prime breakdown as a fixed set of coordinates. This allows us to solve practical challenges. Suppose we want to calculate the total number of positive divisors for a massive number n. Mathematically, this is denoted as tau of n. This equation on screen is the formal prime factorization formula for any integer n. It maps out its distinct prime bases and their respective exponents. Any divisor of n must be constructed by selecting a specific power of each available prime. That selection ranges from 0 all the way up to the prime's maximum exponent. We can frame this selection not as a tedious division problem, but as a rapid combinatorial choice. It is like choosing ingredients from a menu. Here is how that maps algebraically. We expand the choices into polynomial brackets. Each bracket represents all the possible powers of a single prime. To find the total combinations, we simply multiply the number of choices together, the exponents plus 1. The brackets collapse, revealing the final formula for tau of n. By understanding the unique prime DNA of a number, we bypass the need to blindly test divisors. We elevate basic counting into an elegant, instantaneous combinatorial operation. Let's set up a test of our structural logic. We are going to determine the exact number of trailing zeros in 158 factorial. 158 factorial is an immense value. Conceptually, it is the product of every single integer from 1, multiplied all the way up to 158. A trailing zero is only created at the end of a number when there is a factor of 10 in the final product. If we break the number 10 down into its prime DNA, we see it requires exactly 1 2 and 1 5 to pair up. Factorials have a predictable structure. Because every second number is even, there is an overwhelming abundance of 2s available in the sequence. That gives us a strict bottleneck rule. The total number of 10s, and therefore the number of trailing zeros, is entirely bottlenecked by how many 5s exist in the prime factorization of 158 factorial. Instead of trying to calculate the astronomical value of the factorial, we only need to hunt for multiples of 5 within the sequence. This brings us to this grid of numbers from 1 to 158. We start with the base layer. Using the floor function, we divide 158 by 5. This reveals there are exactly 31 multiples of 5 in the sequence. Next, we look for the hidden second layer. Numbers like 25, which is 5 squared, contribute an additional 5. We divide 158 by 25 to find 6 extra 5s. Finally, we check for the deepest third layer. The number 125, which is 5 cubed, contributes a third 5 to the total. We divide 158 by 125, finding exactly 1 extra 5. The math yields a definitive answer: 31 base 5s plus 6 secondary 5s plus 1 tertiary 5 equals exactly 38 trailing zeros. By stripping integers down to their bedrock axioms, Euclidean remainders, structural divisibility, and unique primes, we eliminate brute force calculation. This gives us the mathematical power to dissect, map, and conquer massive numerical structures with mathematical precision.